Okay, hello and welcome back everybody. This is the worked example section for eigenvalues and eigenvectors. And I'll comment that we won't be seeing examples of eigenvalues or eigenvectors in infinite dimensional settings, mostly because the important ones, the important cases, are number one, tricky, number two, involve derivatives, and hence number three, belong in a differential equations course. But if you're interested in those, you know where to look. And we will tackle a couple kind of implicitly when we do deal with our differential equations that are important, in this course, but we won't be trying to do them explicitly on days like today. So we are really only handling the matrix cases. Matrix cases in finite dimensions, and let's recall our method, step-by-step method for finding eigenvalues and eigenvectors. So first, we compute the determinant of m minus lambda times the identity, set it equal to 0, and solve for all lambda in the complex numbers. This was called our characteristic equation. And the solutions are our eigenvalues. Secondly, for each eigenvalue, set up m minus lambda times the identity against a vector x equals the vector 0, and solve for a relationship between the entries in this vector x. It's always a relationship, it won't be specific values. In step 3, set all undetermined values in x to be 1. Now, in fact, you can set them to be any non-zero number, but 1 is almost always the right choice. And because I've kind of included the for each lambda in C in step 2, for each lambda in C applies to step 3 as well, and we can kind of skip step 4. That's really our step-by-step process. Should feel familiar from last video. So we're just going to jump right into things and tackle really just two cases today, a 3x3 matrix and a 2x2 matrix. By the way, these only make sense for square matrices. So maybe I'll make a little asterisk up top over here. Only makes sense for square, which is when rows equals the number of rows equals the number of columns. Matrices. This is something special about both invertible matrices and eigenvalues, eigenvectors. Square matrices are really the ones that people like to consider. So we'll do a 3x3. Let's say find all eigenvalue, eigenvector pairs for my 3x3 matrix 6, -1, 5, 2, 0, 2, -8, 1, -7. So let's just go ahead and follow our steps. We're going to compute and solve the characteristic equation which will be the determinant of the matrix minus lambda on the diagonals. So I'll just start with subtracting lambda from the diagonals. Right? This is really me subtracting lambda times the identity. And then I'll include my other terms, -1, 5, 2, 2, -8, and 1. Now this is definitely one of the reasons why calculating determinants was important from the beginning. What do we do for a 3x3 is we grab each of the terms on the top row and multiply by the determinant of the submatrix. That's the first term in the top row, second term in the top row, submatrix is there, second term was -1, times the determinant of the submatrix, 2, -8, 2, -7 minus lambda. Then the third entry is a 5 with the submatrix in the bottom left. So we have a 5 times the determinant of the submatrix, 2, -lambda, -8, 1. Then we follow with a plus minus, so there's two minuses there, plus signs. Let's go ahead and compute these. So I've got 6 minus lambda. Then that other determinant, it's always AD minus BC. So we've got -lambda, -7 minus lambda, minus BC, -2 times 1. Second term, minus -1, so plus 1, times the determinant of AD minus BC. So we'll have 2 times -7 minus lambda, minus -8 times 2. Then we're left with 5, determinant AD minus BC. And that'll give us 2 times 1 minus -8 times -lambda. If I go ahead and simplify, sometimes a lot of work to simplify, but that's the price of math. Go ahead and distribute the minus lambda to both terms. It looks like I've got a positive 7 lambda and a positive lambda squared, as well as -2. And then have a 1 times distributing the 2 to both terms. Looks like I have -14 minus 2 lambda. Then I've got -16, so plus 16. And then my last term is going to be plus 5 times 2. Looks like negative, negative, negative. 3 negatives becomes 1 negative, and I have -8 lambda. I have to go through a little bit more work yet again to simplify. So I'm distributing 6 to all 3 terms, and minus lambda to all 3 terms. The 6 on the 7 lambda gives me 42 lambda. 6 on lambda squared gives me 6 lambda squared, and 6 on -2 gives me -12. Meanwhile, minus lambda on 7 lambda gives me -7 lambda squared. Minus lambda on lambda squared gives me minus lambda cubed, and minus lambda on -2 gives me plus 2 lambda. Meanwhile, I can just eliminate the parentheses in the middle term as -14 minus 2 lambda plus 16. And finally, I'll distribute my 5 to both final terms and end up with plus 10 minus 40 lambda. And I promise it's all going to work out for us. If I just look at all the terms with a lambda cube in them, there's only one, so I have minus lambda cubed. All the terms with lambda squared in them, I've got 6 lambda squared minus 7 lambda squared, total of -1 lambda squared. All the terms with the lambda in them, I've got 42 lambda plus 2 lambda minus 2 lambda minus 40 lambda, so the 2's are canceling. And at 42 minus 40, I'm going to be left with a positive 2 lambda. And then in terms of the single digits, I've got -12 minus 14, also known as -26, plus 16 plus 10, also known as positive 26. So all 4 of those are going to cancel, and I'm left with a plus 0. So even though it really was a bit of a nightmarish calculation, this is definitely simplified a fair bit. And in fact, it's simplified so much that I can factor out a minus lambda. Notice every term at least has a lambda in it. You can always factor out a -1 from something. Pull out a minus lambda, what I'm left with is lambda squared minus, plus lambda actually, -2. And so if we're looking for when this is equal to 0, it's really not bad that I was able to factor that out, because the lambda equals 0 case comes for free then, and I can just take a look at this quadratic and check my quadratic formula, which is going to give me negative b plus or minus the square root of b squared minus 4ac all over 2a, where it looks like a is 1, b is 1, and c is -2. So b is 1, I get -1 plus or minus the square root of 1 squared minus 4 times 1 times -2 minus -8, also known as plus 8, divided by 2 is going to be -1 plus or minus the square root of 9 negative 1 plus or minus 3 all over 2. Negative 1 minus 3 is negative 4 over 2, gives me a 2, negative 2. Negative 1 plus 3 is positive 2 divided by 2, gives me a 1. So I've got 3 cases of lambda. I have a 0, a negative 2, and a 1. In step 2, for each of these lambdas, I'm going to solve the eigenvector equation. Say for each of, let's do my lambda equals 0 case here, my lambda equals 1 case, and my lambda equals negative 2 case. We're going to solve the following. M minus lambda, which in this case is 0 times the identity, on x equals the 0 vector. M minus lambda, which is 1 times the identity, times x equals the 0 vector, and m minus lambda minus negative 2 plus 2 times the identity on x equals the 0 vector. And unfortunately our matrix was quite large. Let's remember what it was. It was 6, negative 1, 5, 2, 0, 2, negative 8, 1, negative 7. And in the first case, because I'm subtracting 0 from the diagonals, I really don't have to include that subtraction. So I'm just left with that matrix acting on x, which I'll just call x1, x2, and x3. And that's set equal to 0, 0, 0. In the second case, the matrix will have to subtract 1 from the diagonals. Against x1, x2, x3 is equal to 0, 0, 0. And in the third case, I'm subtracting negative 2, also known as adding 2, to each of the diagonals. Against x1, x2, x3 equals 0, 0, 0. So if I go ahead, I can just replace these with their values of 6 minus 1 is 5, 0 minus 1 is negative 1, negative 7 minus 1 is negative 8. And I can replace these with their values as well. 6 plus 2 is 8, 0 plus 2 is 2, negative 7 plus 2 is negative 5. And I'll go ahead and change these to have the same color so that they all agree. Now if I just compute the matrix vector multiplication, I have my 3 rows in the matrix against the vector of x's. And what I end up with is 6x1 minus x2 plus 5x3. I end up with 2x1 plus 0x2 plus 2x3. And I end up with negative 8x1 plus x2 minus 7x3. And all of these are equal to the 0 vector on the far right. If I want to go ahead and solve this system for a relationship between x1, x2, x3, I'm going to give myself a little more space. So let's go ahead and solve this system. In the first case, I can rearrange to solve for x2 just by bringing x2 to the right-hand side. That gives me that 6x1 plus 5x3 is x2. And I can use that value of x2 as x2 in the latter two cases to rewrite those as 2x1 plus everything that I just got for x2. 6x1 plus 5x3, but of course that was multiplied by a 0. And then I can add x3 to x3 equals 0 is my second equation. My third is negative 8x1 plus everything that I just solved for x2 is 6x1 plus 5x3 minus 7x3 is 0. And I can rearrange the second row to be solved for either x1 or x3. Let's just rewrite it as 2x1 is negative 2x3, or the relationship x1 is negative x3. And knowing that, I can replace that value for x1 into the first equation, or the third equation, as well as the first equation. And I end up with, in the first equation, 6 times negative x3 plus 5x3 is x2. And in the bottom equation, I end up with negative 8 times negative x3 plus 6, and x1 is negative x3, so 6 times negative x3 plus 5 times x3 minus 7x3 is 0. What I end up with in the bottom equation, if I simplify everything, I have a total of 8x3 minus 6x3 is 2, plus 5x3 is 7x3, minus 7x3, I end up with 0 equals 0. And so unfortunately, this line is now meaningless. It's not false, it's just not going to give me any information. Maybe I'll call it informationless. But the top line here will give me some information, because if I simplify that line, I have negative 6x3 plus 5x3. Negative 6 plus 5 is negative x3 is x2. And this is what I mean by the fact that I always end up with a relationship. I've just found out that x1 is negative x3, but I also know that negative x3 is x2. And so here's my relationship, which means the vector x1, x2, x3, underneath the relationship, I can replace x3 with negative x1 if I want to. And I can replace x2 with x1, just because x3 is negative x1 and x2 is x1. So then this x1, x1, negative x1 is my eigenvector for lambda equals 0. I can then repeat for the lambda equals 1 case with my new matrix, where I'm doing the matrix vector product of these three against my vector. It's going to give me the system of equations 5x1 minus x2 plus 5x3 is 0. It's going to give me on the middle row 2x1 minus x2 plus 2x3 is 0. And on the bottom row, negative 8x1 plus x2 minus 8x3 is 0. And I get to play the same games I played before. Grab this entire system, pull it over here, solve the first one for x2, as x2 is giving me 5x1 plus 5x3. I can use that in the second line, since I have solved for x2. I can use that in the second line there, and in the third line there. So the second line now reads 2x1, instead of minus x2, I'll write it as minus everything that was above, 5x1 plus 5x3 plus 2x3 is 0. And the bottom line now reads negative 8x1 plus x2, but I'm replacing from above, 5x1 plus 5x3 minus 8x3 is 0. Combine my like terms, it looks like I've got 2 minus 5x1, so that's negative 3x1, and then another 2 minus 5x3, negative 3x3 is 0, or in other words, x1 is negative x3. If I use that in my bottom row, I have negative 8 plus 5 is negative 3x1, and negative 8 plus 5 is minus 3x3 equals 0. That's giving me exactly the same relationship, which is always going to be true, right? This informationless statement will always occur in eigenvalue problems. And so both of those are valid, as well as the original equation that we have. But now that we know that x1 is negative x3, this original equation simplifies for me, telling me that x2 is 5 negative x3 plus 5 x3, and those are just going to cancel and tell me that x2 is 0. Therefore, my relationship is that x1 is negative x3 and x2 is 0. Therefore, my vector x1, x2, x3, I can replace x2 with a 0 and x3 with a negative x1. This is my eigenvector associated to the lambda equals 1. Let's go ahead and do it one more time. For lambda equals negative 2, I have my matrix against my vector, which gives me the system of equations 8x1 minus x2 plus 5x3 equals 0. I have 2x1 plus 2x2 plus 2x3 equals 0. And I have negative 8x1 plus x2 minus 5x3 equals 0. If I go ahead and solve the first equation for x2, what I'm left with is x2 is positive 8x1 plus 5x3. And then I can use this value of x2 in the other two equations right there and there, which is going to give me 2x1 plus twice what I've just calculated, which is 8x1 plus 5x3 plus 2x3 is 0, and my bottom equation, negative 8x1 plus what I've just calculated, 8x1 plus 5x3 minus 5x3 is 0. And we immediately see that this bottom line, negative 8x1 plus 8x1, reduces to that case of 0 equals 0, so informationless, which is okay. One of these will always be informationless. My middle line reduces to, it looks like I've got 2x1 plus another 16 of those, so a total of 18 x1s, and it looks like I have 10 x3s plus another 2 of those, so I have 12 x3s equals 0, which is only going to be true. I can divide both sides by 6, and I get 3x1, and bring my x3s to the right, negative 2x3, or rather that x1 is negative 2/3 x3. Now that I have that relationship, I can use it up there to give me that we have 8 copies of negative 2/3 x3 plus 5x3, which gives me negative 16/3 x3 plus 5 x3, which is 15/3, or rather negative 1/3 x3 total. So my relationship now, I know that x1 is negative 2/3 x3, and I know that x2 is negative 1/3 x3. So my vector x1, x2, x3, I can replace both x1 and x2 with their versions of x3 of negative 2/3 and negative 1/3. This is the eigenvector associated to lambda equals negative 2. At step 3 then, I let all undetermined values be 1. And so my first eigenvector was this one, x1, x1 minus x1. I'll go ahead and let the undetermined values be 1. So instead of x1, x1, and minus x1, I'll just go with 1, 1, negative 1, associated to lambda equals 0. My second eigenvector was x1, 0, negative x1. So that'll become 1, 0, negative 1, associated to lambda equals 1. My third vector is seen above, negative 2/3. I'm going to let x3 be 1, negative 1/3, x3 be 1, and 1, associated to lambda equals negative 2. So these now are my collection of eigenvalues and eigenvectors for my 3x3 matrix that I started with. Now, because it was a 3x3 matrix, I was expecting to have 3 of these, and that is exactly what I ended up with. Let's do one easier example, because the 3x3 cases are definitely tricky. Let's do one more easy example. Find all eigen pairs for the matrix 3, 4, 4, 3. 2 by 2 is quite a bit easier. We'll find that out now. We're going to compute the determinant of 3 minus lambda, 4, 4, and 3 minus lambda, which will be 3 minus lambda squared minus 16, which will be 9 minus 6 lambda plus lambda squared minus 16. You can see I've been around the block with algebra before, which is going to be lambda squared minus 6 lambda. 9 minus 16 is negative 7 equals 0. We're going to use the quadratic formula here. Negative b is negative 6, so 6 plus or minus the square root of b squared, 36, minus 4ac, there's a negative sign on c, so we have plus 4 times 7 times 1, 28, all divided by 2a. So we have 6 plus or minus the square root of 64, divided by 2 is 6 plus or minus 8 divided by 2, or rather 14 over 2, and negative 2 over 2, also known as 7, and negative 1. So these are our eigenvalues. And then for each of these, in step 2, we set up the eigenvalue equation. So in step 2, for lambda equals 7, we compute 3 minus 7, 4, 4, and 3 minus 7 against x1, x2 equals 0, 0. And for lambda equals negative 1, we have 3 minus negative 1, 4, 4, 3 minus negative 1 against x1, x2 equals 0, 0. And if I want to replace the diagonals with evaluating those, I have a 3 minus 7 is negative 4, 3 minus 7 is negative 4, 3 minus negative 1 is 4, and 3 minus negative 1 is 4. At this stage, if I compute the matrix vector product, I have the system negative 4x1 plus 4x2 equals 0, along with 4x1 minus 4x2 is 0. This system immediately gives me that x1 is equal to x2, and a redundant term on the bottom as well. And so my eigenvector, x1, x2, underneath the relationship x1 is x2, just becomes x1, x1. And I can do the same on my later matrix vector calculation to give me 4x1 plus 4x2 is 0, along with 4x1 plus 4x2 is 0, and that immediately gives me x1 is negative x2, and a redundant x1 is negative x2. The relationship then, x1, x2, becomes x1, negative x1, as the eigenvector associated to lambda equals negative 1. In step 3, I go ahead and let both of my x1s be 1 everywhere, and I recover 1, 1 as my eigenvector associated to lambda equals 7. And I recover 1, negative 1 as my eigenvector associated to lambda equals negative 1. And that's all I have. Pretty straightforward, although it is one of the more complicated calculations of the semester and also one of the more important. Fairly straightforward, so I hope you enjoyed those. See you in the next one. Bye.